We went through this kind of hopefully decent motivation for this puzzling world of hadrons and nuclei in the context of QCD and the quarks and gluons. And we started talking about how we actually access these things physically. And the way we do it is with scattering experiments, such as here at Jefferson Lab, uh, where we have an electron beam that we hit on some sort of target, or at the LHC, where you have two proton beams colliding, head on. And that gives us a bunch of particles, which we then analyze for a long time, try to really pin down all the physics of how this reaction comes about, and try to detail what physics is hiding inside these complicated nuclear reactions. So we started talking a little bit about scattering theory. Here, we have some simple scattering experiment with the pi and proton hitting each other, and yet you get this very complicated cross section, which is just a probability distribution measure, where you see various bumps in the observable, which corresponds to this kind of spectrum of these strong interactions. And in the hydrogen atom example, we saw kind of this discrete line spectra where the energy levels were very sharp and kind of pinpointed. Here, you would kind of say, okay, these peaks are corresponding to these kind of spectral values here, but they don't look as sharp as what we would see in electromagnetism. They're very broad peaks, and sometimes they're very, not peaky at all. Sometimes they're dips. And what's really going on here, and the fact is that QCD interactions are a bit more complicated. So there's a lot of dragon hiding underneath this process, which we are trying to tame. Um, so we went through kind of the fundamental object quantum mechanically that we want to understand is the S matrix, which is the evolution operator for some initial configuration of particles going to some final configuration of particles. And this S matrix element gives you a probability measure, as in all quantum mechanical amplitudes. Um, and the goal of phenomenology is to take experimental data and fill in this S matrix. The goal of theory is, can we compute these S matrix elements given the theory? And I'll today kind of come about it from the point of view of, let's have some experimental data and look at properties of the and getting these S matrix elements out, these scattering amplitudes, and then looking at their properties based on these fundamental principles of physics within scattering theory. And then tomorrow we'll go about it in the reverse way, which is, okay, now instead of taking some experimental data, let's say, and putting a bunch of constraints on the amplitude to try to get out the spectrum of the underlying interaction, can we compute that from first principles QCD? And we will do that with the QCD, or with lattice QCD, and I'll kind of map out the pathway of how we do that and some of the tools that we use. And I won't talk at detail about what lattice QCD is. There's some other talks in the school that will go through some of those details of how to get out some of the observables there, but we will discuss how to take lattice QCD results and convert them into these scattering amplitudes, since there's, as I'll illustrate maybe today, but definitely tomorrow at least, why calculating scattering amplitudes from lattice QCD is not as straightforward as we would like, and as is the case of, say, quantum electrodynamics. So I'm going to go back through the idea of how we associate particles with some mathematical object, because it's an important point. So if you've taken quantum field theory, this may make sense. If you haven't taken quantum field theory, no worries. Kind of just accept this as some sort of truth of how we connect particles we see in nature to some mathematical object. And then as you go through your physics studies, if you're interested in this sort of stuff, you'll kind of get a bit more background information about how this comes about. Because I'm sweeping a lot of these details under the rug of how we go and get out mathematical forms like this, but with the proper training as it comes about, which takes more time than what I have here to show, you'll hopefully get the idea. But at least I hope if you could just accept a few pieces of what I'll call facts of how these things work, and if you accept them, then hopefully you can at least get an idea of how these things can be used. So if you have a stable particle, and then if we're turning off the electroweak interactions and just dealing with strong interactions, the pion is a stable particle. The proton is a stable particle in either case, in full physics or in a case when we turn off the electroweak interactions. In that example, the neutron is also a stable particle because it only decays via beta decay, and for turning off electroweak, don't need any of that. You can also have bound states. So one example I'll talk about later is the deuteron, which you may know of as the simplest nucleus of the that exists. So if you have a proton and neutron, they can weakly bind together into a stable particle called the deuteron, and it makes up a small abundance of the hydrogen that we have here on Earth. So if, like in water, which is, two hydrogens and an oxygen atom, a small percentage, like 4% or something like that, the proton in the hydrogen atom is not a proton, it's a proton-neutron bound state, the deuteron, which is just chemically it works the same way, but within nuclear physics, there's some differences. So even composite particles that are long-lived, so composite particles that live forever, stable particles, all have this type of form where if you have a freely propagating stable particle, in this example here, the pion, the amplitude, the probability amplitude for such a process is given by a pole. So if the and by pole here, I mean if you think about 1 over x in typical mathematical language, uh, as x goes to 0, the function diverges, at that asymptote. We call this in complex analysis a pole singularity, because you can extend this idea to the complex numbers. And the location of this pole, the location of this asymptote is the particle mass. So for the pion, this is a very simple concept. And here's a kind of cartoon illustration of what we mean by a particle mass. It's a pole of some probability amplitude, scattering amplitude. For particles which have a short lifetime, which decay, such as the rho meson, um, in order to quantitatively describe those things arising from scattering amplitudes, these resonances are poles still, but they're now poles in the complex plane of energy. So here we have the energy, the real axis energy here, and the particle pole for the pion is a pole singularity for real energies. Here, if you solve for when this denominator is 0, you have an imaginary component, and the pole location is in the complex energy plane. So we're extending this idea of physical energy to complex energies, and this is where complex analysis starts kind of creeping in its head. And so if you have two pions which interact and make a shortly lived rho meson, it then decays away to two pions, and the probability amplitude will look something like this. So here I'm plotting the modulus of the probability amplitude, it's a complex number. And you see here that there's a bump in the spectrum, and the width of the bump, the full width at half maximum, is roughly related to the decay width, and the location of the peak is roughly located to the mass. Sometimes you'll see, especially in old experimental analyses or kind of weak theoretical arguments, I'll say, they often use bright Wigner parameters or bright Wigner parameterizations, which I will touch upon, and they'll use kind of these parameters here to say, okay, at the peak location, this is the particle mass, and at the width of this peak here is the decay width, which is related to the inverse time. That's true for very narrow resonances, but in general, the most rigorous way we can define them is the location of the pole singularity. So here I'm kind of illustrating a narrow resonance, but we can back that up and be a bit more general and just really wherever the pole singularity is, even for a very deeply or a very wide resonance, so one that decays very, very shortly, it may appear as a dip, it may appear as a bump, it may appear as some weird object if you have multiple interactions happening all in roughly the same energy scope. The amplitude itself can look very complicated from this kind of cute, simple picture. However, the key idea is that resonances are poles in the complex energy plane, just like bound states or stable particles are poles in the complex energy plane, except it's not for complex energies, it's for real energies. So um, if we then think about this, like, okay, this doesn't look like a pole, this looks like just like a bump. Where's the pole at? Well, if we extend the idea of energies to complex energies, so here, this is the real energy axis, and this is the imaginary energy axis, and the vertical axis here is the modulus of S squared, or I'm sorry, the modulus of S. You see here that the bump, this red bump here corresponds to this black line here, which would be, you can think about as the shoulder of this pole singularity, which occurs slightly off the real axis, roughly here, and you see this divergence happening, which is very characteristic of a pole singularity. So the pole singularity exists, but it happens in the complex plane. So if you think about, you have this complex amplitude here, and maybe it's not so simple as this form. However, near the pole, it has to kind of take on this form. So you can do this analytic continuation, this extension of your energies to this complex plane in order to search for these poles. And that's what we do in Hadron spectroscopy phenomenology, is we determine the S matrix element, the scattering amplitude in some fashion, either fitting to experimental data with some flexible parameterization that respects the symmetries and the physical laws that the scattering process must have, or we compute the scattering amplitudes directly from QCD, which is an indirect process, as I'll say, but it mimics very much to what's done in experimental data. You can then you fix everything on the real energy axis, which in experiments, that's all we have access to is real physical energies. And then once you have an analytic representation for your scattering amplitude, you then use your knowledge from complex analysis to let the energy become a complex value, and you can find the pole location. Then you can say, okay, here we have found a particle in this interaction. And what does that mean? We can then quantify properties of it, its mass, its decay width, lifetime, what its spin parity is, and all kinds of interesting stuff. I'll show cartoons like this very occasionally throughout today's lecture, where we can plot this kind of 2D image where the imaginary energy axis is the vertical and the real energy axis is the horizontal. If you have two particles which can start scattering, the minimum energy in which they can start scattering is their threshold energy, which is just the sum of their particle masses. This is this white dot location here. And then as you increase the energy, the scattering region is given by this gray line here. So that's all the available energies that the particles can scatter. Stable particles, so bound states of that scattering process, an example being if you have neutron-proton scattering, the neutron and proton can bind to form the deuteron. The deuteron would have to appear as a real energy bound state pole singularity, and that will be below the scattering threshold. So this blue dot here would correspond to where the deuteron would be. If you have an example like the rho meson, where it's a resonance, a pole singularity in the complex plane, then this red dot here would be kind of a characteristic location for it. You're off in the complex plane some distance, which is roughly corresponds to the decay width divided by 2, and the distance from 0 point, it would be the mass of this resonance. So when we plot these things in the complex plane, these are the general features we'll see: the threshold location, any bound states or stable particles below threshold, resonances off in the complex plane. And I'll say there's a little caveat to this, and I'll go through an example as we start forming what the properties of the scattering amplitude are, and then the scattering regions on the real energy axis. So this is for a very simple type reaction. As I kind of illustrated, more complicated processes have a lot more subtle features. If we go back for a second to our pion proton scattering here, you do see, if you kind of zero in on this energy window here, you see this kind of peak-like behavior. So, okay, that's very similar to what I just described. But then you see, as you scan up in energy, various other amounts of like little bumps or dips or stuff. So this is just telling you have more complicated interactions than a very simple kind of quasi-bound state forming and then decaying away. I won't go into details about disentangling all these kind of coupled interaction effects. But we can do that. It just involves extending these ideas to where you have multiple interactions happening simultaneously. If it's something that sounds interesting to you, I'd be happy to talk more about it, either offline or get you involved in some sort of research project where you can study that. All right. This this little cartoon has to play again. Okay. So the idea from a phenomenological point of view is you have some scattering experimental data, which you then fit with some analytic models that you come up with respect all the symmetries. And that will be the next part, which is building in what scattering theory tells us about how we can form these parameterizations that are that are independent of any sort of interaction so you're not biasing against, okay, I'm assuming that the scattering potential is of this form. No, we're going to do everything as model independent as possible and just form rigorous parameterizations that satisfy scattering theory principles. Once you have that fit, you have essentially determined some specific S matrix element. The S matrix element is then using the ideas from complex analysis to take real energies and go to complex energies through analytic continuation. You can then get out the spectrum. All right. So this is where I wanted to end yesterday. And as I switch slides, maybe I'll field if there's any questions. Anyone? No? All right. So now we're going to keep building upon this and now start kind of forming some more mathematical statements about this and then see how we can play with these ideas in our Python notebooks. So, as I just said, the excited hadrons are not just stable particles or resonances coupling the multi-particle decay modes. You have these very cool bump-like features and dip-like features and, kind of intertwined. So how to distinguish all these effects. And we're going to build upon this idea of rigorously defining Bound states and resonant states within the context of scattering theory, which uses a variety of principles in order to constrain the form of the scattering amplitude, which that can be used in data analysis or make predictions for the behavior of the scattering process near certain energy regions. So one is symmetry. We're generally dealing with a relativistic system. So Lorentz invariance, which is the symmetry of kind of relativistic frame independence, is going to be an important constraint that we build in, which just means we're going to, all the energies we'll be dealing with in momenta will be relativistic versions. Often there's other symmetries like CPT symmetry, which is charge conjugation parity and time reversal symmetry, which allows us to relate antiparticles and particles as very closely related objects. Flavor symmetry, so in nuclear physics, especially when you close off the electroweak transitions between different flavors. So this is if you have a kaon that has strangeness, so has a strange quark in it, it can't transmutate to a particle that doesn't have, or a set of particles that doesn't have the strange quark in it. So this is a flavor symmetry. If you turn on electroweak interactions, you can have that, but we're interested in turning those off in a moment. Baryon number, so you can't have a proton and pion go to, say, 2 pions. You need some sort of baryon to continue on in the final state as well, so it's important symmetry. And there's a bunch of other ones that may exist that are important for your reaction of interest, electric charge being conserved, so on and so forth. Another aspect that is very important is under the umbrella of unitarity, which I would say is a consequence of probability conservation. So as you have some process, so some initial, say, 2 particles interacting, and you have some S matrix amplitude for two final particles, and you can have a different one for, say, two other particles or three particles or so on and so forth. If you sum over all the possible transitions that these two initial particles can go to, then that total probability of adding up all those individual processes must be 1. And this implies that the S matrix is a unitary operator. And if you've taken quantum mechanics, you may know that, unitary matrices, unitary operators are very important because that's what conserves those are the type of operators that conserve probability. And since that's the main object or the main observable we get from quantum mechanics is probability distributions, you want to conserve probability. There's analyticity, which is a general term for looking at how the amplitude behaves as a function of complex energies. So I already kind of mentioned that complex energies are important, especially for defining resonance states and how we quantify these things. The features of the scattering amplitude have to be these analytic functions in the complex energy plane up to some well-defined singularities that can exist. This can be bound states, or as I'll show shortly, branch cuts, which come from pair production of particles. And this ultimately, the physical consequence of why these amplitudes must have specific analytic forms comes from causality. So you want, cause and effect to be preserved, and that's one of the tenets of a relativistic local system. Crossing symmetry is yet another one. So how does CPT symmetry really impose how scattering amplitudes are related between particle and antiparticle scattering processes? And this is just kind of another way to constrain how these general scattering amplitudes, which I write as a blob here with some number of incoming lines and some number of outgoing lines. This is our general scattering amplitude. In these lectures, I'll focus mostly on just unitarity, since this offers a wide variety of consequences, which we can immediately apply and get some information out. Of course, there's assumed Lorentz invariance and some other symmetries. I won't go into detail with too many very complicated type of particles, mainly stick with scalar particles and maybe some kind of ignoring the spin of protons and neutrons. And then there is a lot of work in kind of imposing these type of features as well, but I won't talk about that here just for time. So these amplitudes are complex functions of energy, and it can pose difficulty in generating parameterizations in order to fit experimental data or some lattice QCD generated data. And we want to be able to restrict the allowed forms of these amplitudes, imposing as many physical constraints as possible. So scattering theory here is one way to do that. And unitarity, as I alluded to, if you have some probability distribution for some initial state alpha going to some final state beta, which is related to the modulus squared of the S matrix element for alpha and beta, and you sum over all the possible outgoing final states, then this probability distribution must be 1. So you're summing over all the different probabilities, and that has to give 1 here. So this implies that that this S matrix here is a unitary matrix. In order to preserve the probability, we can write this S matrix element as just mathematically as in terms of 1 plus this blob here, which this blob here I'll define as m in a little bit, is the alpha to beta scattering amplitude. This 1 here corresponds to no scattering, so there is the possibility if you have two particles going at each other that they miss and they don't talk to each other at all, and this is the case of no scattering. You're not really interested in what happens with no scattering, so we'll break up this S matrix element to the case where there's no scattering and just focusing on this guy here. This constraint in turn, and I'm schematically showing it here, I'll be a bit more detailed later, implies that the imaginary part of this amplitude here is equal to the sum over all possible states in which you have some particle with alpha coming in, going to any n particle intermediate state, multiplied by the same amplitude going to beta times the complex conjugation of that amplitude. So this constraint here from unitarity imposes that the imaginary part, and we know that scattering amplitudes are complex numbers in general, complex functions. Unitarity imposes that the imaginary part is constrained by some complicated relation. And in general, this is a very complicated relation that can exist. We'll be focusing on a very simple example of two-particle scattering and what does this type of relation give us. And in the case of two-particle scattering, what you can show, and what we will talk about, is that the scattering amplitude is related to one real number, which is known as the phase shift. And if you take quantum mechanics, scattering and quantum mechanics, hopefully this idea is familiar, and some kinematic factor, which is known. So if you have two-particle scattering amplitude, you may think it has a real part and imaginary part. Well, that's two independent numbers. However, unitarity restricts that the imaginary part is fixed by some other amplitudes, so we end up having to only needing one real number to describe this scattering process. I thought let me skip this for now because this deals with this context and no, let me not skip it. Let me go through this idea. So if we, yeah, let me skip this for now. I'll bring this back up later. This was supposed to be for tomorrow. Sorry. So the, oh, I apologize. I put this in the wrong section. Okay. Yeah. So let's go to here, and then we'll go back to the scattering amplitude or the complex analysis stuff in a moment. I apologize for that. I put these slides in the wrong location. So the scattering amplitude, which I'm calling M here, characterizes the probability of an interaction to occur. And this M here is that gray blob, which is the S matrix minus the case when there's no interaction. So if you have two particles coming in, which is the case we'll be focusing on, two particles come in, they do some interaction, and they go out. The scattering amplitude itself is a complex number of energy. And here I'm going to write the energy in the center of momentum frame. So the center of momentum frame is when two particles go back to back. And this little star notation here is just to remind us that we're in that center of momentum frame, just some convention that people came up with years ago. So the scattering amplitude is a function of energy, and we're going to be in a Lorentz frame where the particles are going back to back. The scattering amplitude has real and imaginary components. Here I'm showing a case for a Bright-Wigner-like resonating system where you have the scattering amplitude real part in red and the imaginary part in blue. The threshold energy is the point at which the scattering can occur. So if we have equal mass particles, then the threshold energy is twice the particle mass, and here the x-axis is in units of the particle mass. And you see some general features. The physical energy starts at 2 here, but if you do an analytic continuation, excuse me one second. Excuse me one second. I apologize for that. Someone came to my door and it is causing a stir. All right. So if we push the energy from the real energy physical region slightly below the physical region, we see here this little cusp-like behavior in the scattering amplitude, which corresponds to the location where these two particles can be pair produced. And That is going to be an important feature for us to describe the analytic properties of this scattering amplitude here. The probability distribution is just simply related to the modulus of m squared, which you would get something like this. And this kinematic factor rho here is just a simple it's just a simple way to make this uh, plot here proportional, attain a maximum at 1 where the maximum location occurs. Sorry, I'm a little thrown. All right, so um, the as we said, the S matrix is a unitary operator coming from the probability from some initial state going to some final state as 1. After some work, and this is what I was schematically showing with those gray blobs, you can show in this kind of limited energy region, which is called the elastic scattering region, that the imaginary part of M is equal to a factor, a kinematic factor called rho, which I'll define in a moment, and the modulus of m squared. So this imaginary part is valid for the center of momentum energy greater than the threshold energy. And if we think about some scattering system where you have the 2-particle threshold and the 3-particle threshold, this relation is valid in the region between 2 and 3. So what is this kinematic factor rho here? Well, it's a phase space factor. It's a kinematic function completely known. It characterizes the phase space that 2 particles can propagate. It's defined as some C factor, Q star divided by 8 pi, some convention from some normalization, and E star here. Is C factor is a symmetry factor. If the 2 particles that are scattering are identical, it's 1/2. If they're different particles, then it's 1. So if you have, 2 pi pluses, the symmetry factor is 1/2, and this just means that if you have pi plus going in one direction and pi plus going the other direction, since they're back to back, if you rotate the system by 180 degrees, you can't tell the difference between the 2 particles, and identical particles in quantum mechanics end up yielding these symmetry factors. If they're 2 different particles, then there is no symmetry factor because as you rotate by 180, you can tell which particle is which. E star here is the center of momentum frame energy. And Q star is the momentum between the 2 particles in the back-to-back. So if particle 1 would have momentum Q star, particle 2 would have momentum negative Q star. And because energy and momentum are related in an intimate way, this momentum can be written in terms of the energy of the particles, and the formula here is just given by 1/2 the square root of E star squared minus 4m squared. So immediately here, we see that the imaginary part of the scattering amplitude is related to the module itself and some kinematic factor, which has the square root here. The square root induces some very interesting behavior of the scattering amplitude, which is a general truth, if you will, about about the scattering amplitude. If you've taken complex analysis, you know that the square root function is a multi-valued function, and even just on real analysis, if the energy is above 4m squared, then you're taking the square root of a real number. But if it's below 4m squared, then you have a square root of a negative number, and in the real numbers, that's undefined. So if you do the extension to complex numbers, this can be either positive I or negative I, depending on your convention or definition. This is the multi-value nature of the square root. And it's at this point here, I sent the link in the chat. And we're going to look at first Hadspec X0 complex. So this has some general features about plotting complex functions in Python and some contours and stuff like that. I'm going to go to the very end. So let's first, let me make sure. Is this, well, let me ask this question. Is this text too small for anyone to see?
You might make it just one size bigger. It's not unreadable, but you really gotta
Yeah. Is this better?
yeah, I think that's a bit better.
Okay. Okay. So here, if you're deficient or not as familiar with complex numbers, especially in the context of scattering, there's a couple of references here. There's a mathematical textbook which I very much like because it's geared toward engineering and science. Fundamentals of Complex Analysis by Saf and Snyder. Um, yeah, if you have that book or one similar, all this stuff is in there in some way. In the context of scattering, there's a very useful. It's an old book, but the first chapter has a complete overview of all the complex analysis you need for understanding scattering theory, particle physics, and frankly, I think even in quantum field theory, because all that stuff is related in some way or another. And if it's got a good introduction. It's this book by Burckhardt called Dispersion Relation Dynamics. You can possibly find it very cheap on Amazon or in other ways, which I won't promote. Um, for the square root, there's a blog here which I've taken some functions just because I think it's very nice that you can check out. And here, let's start executing this thing. So I will use Anaconda 3, Python 3. This is all in. Okay, so I've imported a bunch of different libraries. So CMath has complex routines, math, NumPy. Some of these things I won't use here, but they're good to have. We're going to skip this section here on analytic functions. I encourage you to go through it if you're not familiar with it, or some pole singularities, contour integrals. Here we'll deal with the square root function. Okay. So for a general complex number, z, you can write it in terms of its polar form of some radius r and some argument or some phase phi here, so e to the I phi. So if you take the square root of z, you would take the square root of r and then this exponential factor, the half power, and you restrict your phase domain between minus pi and pi. And this is in effect defining um, what you mean by taking, say, a square root of a negative number. Is it positive I or negative I? So here I have a simple function, which is plotting the square root function in a 3D surface. So just a bunch of, making a mesh grid in X and Y between -3 and 3, 50 points. X and Y, the Z max and Z min are between -2 and 2, and then a bunch of different labels and stuff. So if we execute this again, um, the square root function, we can look at the real part and the imaginary part of the square root function separately. The imaginary part here, if you have, so x equals 0 is at this point here. For positive numbers, you have a well-defined square root function, but for negative numbers, you can either be positive some number or negative some number. And this is the multi-value nature of the square root function. This multi-value nature induces what's called a branch cut singularity. So in complex numbers, complex variables, you have pole singularities, which are like 1 over x, and you have branch cut singularities like the square root of x, where for some domain of x, this function is seemingly undefined. So this branch cut here is an important feature of the square root, and it induces this cut behavior in the complex z plane. Yeah, is there a question? Nope. Um, so this same type of square root behavior is showing up in our um, scattering amplitude. So now it's a square root coming from the momentum of the system, and its convention. Okay, so let's still talk about before I go there. So if we look at a domain coloring plot of the square root function, you'll see here, so this is the x-axis and the y-axis, that this thing really is multi-valued here. It's green when you get from the positive side, yet purple when you come from the negative side. So there's a clear discontinuity as you go from positive to negative y. So positive, negative, imaginary part for x below 0, yet it's continuous for positive numbers. And this is the typical mathematical square root function. It is useful to skip this. especially in scattering theory. I said here that this imaginary part exists for the energies above 2m. And what you can show here is that the square root function, where you have the branch cut defined along the negative axis, is not convenient, since what scattering theory tells you is that we want the square root function to be discontinuous along the positive x-axis or energy axis. Branch points of multivalued functions must remain fixed, but the branch cuts can be rotated whatever direction you want that's convenient. So while mathematically the square root function is usually defined to where the negative values are undefined with this, where this branch cut is, scattering theory is telling us, and if you study the stuff in detail, you can see how this comes about in great detail. But it's telling us that we want the branch cut, instead of going to the negative, we want it going to the positive direction. So you can change the orientation of the branch cut by adding, if we look at our z equals r e to the I phi, by adding some arbitrary phase to this exponential, which we're completely allowed to do. And this is what dictates where the branch cut lies. And in this module here, I've defined a new square root function, which I call, where'd it go? Which I call square root, and it has an argument of z and theta. So the square root function here adds an additional parameter theta, which you can dictate where you want your branch cut to lie. So this is adding in that extra phase for your definition of the square root. So the argument here is the angle of z. This is the original angle that is between minus pi and pi, the original mathematical definition. The modulus here is the absolute value of z. And here I'm using numpy to do the angle and absolute value, because often we're going to use vectorization in Python, since loops are very slow, in order to do some manipulation. So I'm using the numpy version here in order to accept that immediately. And then the argument, which is this which is this exponential I times the phase divided by 2, the argument would be the modulus of the argument plus this theta against 2 pi minus theta. So this, I feel like it's a little hard to explain, but if you just sit down and do the math, you can show that you're essentially choosing whether or not where your argument is lying in the 0 to 2 pi range. So we're changing the direction from minus pi and pi and changing it to 0 to 2 pi, which is where the cut structure is. And then we simply define this square root as the square root of the modulus times the exponential of I times the argument over 2. And then we plot the figure looking at 2 pi as where the cut location is, since before the cut was at pi in the complex plane, now we're changing it to 2 pi. And we see that the cut is now along the real axis. And the real part is now the term that has this discontinuity, and the imaginary part, while it is continuous, the derivative is discontinuous. So this square root function is an important feature of the scattering amplitude, since it comes in through this momentum factor, which comes in through this phase space factor. So this phase space factor induces this branch cut behavior of the scattering amplitude, and the branch cut behavior is on the line from threshold to positive infinity, where the elastic scattering region is. All right. Let me pause there and field questions. Any questions?
Could you repeat that last part regarding the phase change to the elastic region relationship?
Yeah, so here, okay, so let's first, so the imaginary part of m, the scattering amplitude, is equal to rho times the modulus of m squared. Rho has this square root function from the momentum in terms of energy. This means that m here itself has this square root like behavior for positive values of energy greater than 4m squared, or positive values of energy squared greater than 4m squared. So in terms of the energy plane, the square root function, when energy is greater than 2m, which is this location here, this scattering region here corresponds to where this imaginary part exists. And the imaginary part exists where the square root function has this branch cut. So this is the reason why we're taking the square root function in mathematics and rotating the branch cut, because scattering theory is telling us that we want it going from 2m, going to positive energies. This may seem a little strange at first, and I agree with you, but if you can hopefully kind of accept these ideas that at least the scattering amplitude has the square root like behavior in the amplitude, then after some work on this, hopefully it makes a bit more sense. It still puzzles me, to be honest, on certain days. But it's really telling you that the imaginary part of this amplitude, when it's non-zero, is along this branch cut here.
Yeah, I see. Thank you.
Mm-hmm. So this is why we're going through this work to rotate the branch cut. So this notebook here has a section on simply rotating the branch cut for the square root function. So then when you look at a domain coloring plot, you see now the discontinuity is in this positive region here, which just aligns with what scattering theory is telling us. So important point about branch cut singularities is that the point at which the branch cut occurs, which is 0 in this case for the square root function, is always fixed. But you can rotate the branch cut in whatever direction you want. So if we look at another example, just copy this. So now so before was 0, now we have 2 pi. Let's look at if that's at pi over 4. Oh, I didn't start up that plot. Oops. Oh, I don't know. Sorry, I'm just trying to make sure I have all these. You should go in order when you're executing these things. There we go. All right. So here, when we input pi over 4, we're now changing the branch cut location to where it's at 45 degrees, but here it's in the negative direction. And I'll leave that as an exercise to you as you try to disentangle how you change the branch cut location, what I did in this function here of why it's going in that direction. And that's because how it's originally defined between minus pi and pi, you have this extra shift you kind of have to do in your head in order to rotate it the direction you want. But yes, you can rotate this branch cut any direction you want. So 3.2 times pi divided by 4, and it will give you some off direction location. So branch cuts can go wherever you want, but the location of where they start is always fixed. So maybe the square root function is important. If you come away from anything from this lecture, square root function is important. Complex variables tells you it's multi-valued, and it has this branch cut discontinuity. So whenever you see a square root function, you should immediately think about that. All right, so this is one feature of the scattering amplitude. Unitarity, which is this general relationship here between the imaginary part of m and this phase space factor and this modulus of m squared, enforces some useful properties of the scattering amplitude. So at fixed energy, so let's take the energy to be fixed, the amplitude is determined by 2 real numbers, and that's the magnitude and the phase. So I'm calling this phase delta and the magnitude the modulus of m. So now if we impose unitarity, if we take the imaginary part of this thing, which is, this thing's a real number, the imaginary part of the exponential comes from the famous relation e to the I, it's Euler's relation, e to the I delta equals cosine delta plus I sine delta, then you'll find you get sine delta coming from here. And you can show then that the modulus of m is fixed in terms of this kinematic function and this phase shift. So that if you combine everything together, the scattering amplitude is at fixed energy is determined by one real number, the phase shift, and this kinematic factor here. So this kinematic factor is inducing this square root branch cut behavior, and this phase shift is detailing essentially the dynamics, because here we're just using basic properties of the scattering amplitude to fix essentially the kinematic relation. All the dynamics for what's happening for a particular scattering process is hidden inside this phase shift. So we've turned our problem of determining two real numbers, the magnitude and the phase, to determining one real number. So that's very nice. And the phase shift for this typical Bright-Wigner resonance-like amplitude would look typically like this, where you have some, in degrees, the phase shift can rise to 180 degrees where the resonance region is located. And for different types of interactions, the phase shift looks different. But if you have this information, which let's say you measure from experiment or determine from lattice QCD, you can feed this into here, rho is known, and you know the entire scattering amplitude. Another relation which is useful is the K matrix representation. If we look at the unitarity relation again, and instead of what we did before, we now divide this by the modulus of m squared, one can show that the imaginary part of m inverse is equal to negative rho. So the imaginary part of this inverse amplitude is equal to the negative of a known function. Well, this just means then that m inverse itself, the inverse scattering amplitude, is equal to some real function minus, because of that negative sign, I, since it's imaginary, times rho. So this K matrix here, which here we're writing in terms of the inverse K matrix, you can rewrite this thing in terms of this expression here, where m is equal to K divided by 1 minus I rho K. I'm just inverting this expression. And in this way, we can see that the scattering amplitude has, again, these kind of two distinct features. One is the kinematics of the two particles propagating at some given energy, and that's fixed by the kinematic factor rho. And then all the short distance, all the short range interactions that happen between the two particles. So this, if you imagine, if you're giving some potential in quantum mechanics, all the potential information is wrapped up into the K matrix. Or if you have some field theory, all the interaction information is encoded inside the K matrix, and all the kinematic information about how these particles propagate is encoded here. So this is the known part, this is the unknown part. This is a real function. So again, one real known function for a given energy. With this relation and the previous phase relation as an exercise to you can show that the inverse K matrix is equal to rho times cotangent delta. In terms of scattering theory, we don't know what this K matrix is. We need to either determine it, just like we need to determine the phase shift from some experimental analysis, or we can calculate it given some theory. In quantum electrodynamics, you can calculate this thing by perturbation theory. In QCD, we will get at this thing from looking at lattice calculations. So these are two useful representations of the scattering amplitude. And now I want to turn to going to the scattering exercises. Hadspec EX1 is on the scattering amplitudes. So the scattering amplitudes, here's some notes, again, with some references that may be useful. A part of the group I'm with, the Joint Physics Analysis Center, hosted some summer schools on fundamentals of scattering theory. There are some lecture videos there if you're interested in. I give a couple of them, but there's some other ones that are really good that if you're interested, check them out. There's some books that may be interesting. So on this, scattering theory is a rather old topic. So there's many papers and books on the subject. The following books I list here I find the most useful. Warning that all these are a bit old. So some notations or some kind of descriptions of how particle physics is outdated here, but the general concepts of scattering theory are still there. A really good book on non-relativistic scattering theory, which it still uses the same concepts we discuss here, but a big connection is just you don't use relativistic momenta, you use non-relativistic momenta, is in this book by Taylor. This is the same Taylor that has the classical mechanics book that is pretty popular. This is a Dover book. Dover books are rather inexpensive. I think you can get this for like $10 on Amazon. If you're interested in scattering theory or plan to work in particle physics or go to graduate school, I highly recommend this book. If you can master everything in this book, going to the relativistic case is very, very simple. It's a very useful book. If you're not too familiar with the kinematics of relativistic systems, there's a book, again, it's an older book, but there is no book that is better, on particle kinematics by Bickley and Kayante. Buying a physical copy of this is very difficult nowadays. There are other ways to get it. I'll leave you to it. But it's a fantastic book. And again, it's one of those things, if you understand everything in that book, you can do theory or experimental particle physics rather easily when it comes to the kinematic aspect, since that has a lot of explanations in there. And if you can master that, you'll have a pretty good understanding of what relativistic collision theories or how relativistic particle kinematics works. So this notebook is concerned with the scattering of two particles, so what we call the general 2-to-2 scattering of spinless particles, so not something like the proton and neutron, something like the pion. Some definitions here which aren't needed at this moment, but in case you're interested in, we're going to be looking at what's called an S-wave scattering amplitude, which is just telling you that the interactions are going to be isotropic, so there's going to be no angular dependence. And this is just kind of a simple example to start off with. So let's start this notebook up. So you can follow along if you'd like, or just watch what I'm doing. So the first thing here is this complex square root. So I showed you a different function before of how to rotate the branch cut. Here's a trick way, if you want to define the square root function to go from, instead of the branch cut being from -infinity to 0, going from 0 to infinity, instead of defining that very complicated function, all you do is you let square root of z go to I times the square root of -z. You can play with this to show that it quickly will switch around the branch cut location, and I'll execute the command and you see that the branch cut has been rotated, and this is just a plotting routine. All right, so the first set of exercises here concerns with two particle kinematics. So I have some kind of definitions here and some suggested exercises you can do. And I'll kind of just point out what's going on here. So the total momentum of the system, I use capital P, which is written in terms of P1 plus P2, which are the individual momenta of the particles. The energies are given by omega, and it satisfies the usual relativistic dispersion relation. So omega is equal to the square root of m squared plus p squared. The center of momentum frame, which is the frame where the particles go back to back, is the frame in which the spatial part of the momentum goes to 0. And again, we use this star in order to indicate that we're in this special frame where the particles are back to back. In this frame, we can define the center of momentum energy squared, which we often label this E star squared as S. This S is often also called the invariant mass squared of the system, or a Mandelstam invariant. Those are just buzzwords for you to be aware of. Really, you can just think about it's the center of momentum energy squared. It's a convenient shorthand. When the particles are identical, as we have in this case, the individual particle momenta we define by Q, and as I showed before, it's equal to 1/2 times the square root of S, which is just E star squared, minus 4m squared. Here are some exercises if you want to show what the relations are for unequal masses, and it just involves doing some manipulations on energy, on the energy momentum relation up here. But in this exercise, I work in units where I set the particle mass equal to 1. This means that every quantity is in terms of the particle mass. So instead of plotting Q star at, say, in MEVs or GeVs, we're plotting Q star in terms of the particle mass. So this is why I have Q star over M here and E star over M, because I'm setting the particle mass equal to 1. This is just convenient. If you want to deal with the proton, you can input the proton directly in here or what have you, and you'll get what the values for the actual particle are. But in this case, it's kind of particle independent. You can deal with any particle you want. So the QCM function, which is this center of momentum, that's the CM for Q, so this would be Q star, you can also define, is 1/2 my square root. My square root is that special function that rotates the square root function, S minus 4m squared. And then here I have a simple plot routine, which just plots the momentum as a function of energy. And you see it turns on that 2. This is where the momentum becomes real, and below the momentum is 0, because it, you know, if you're below the threshold energy, the particles can't be produced. There's an important quantity called the phase space, which we saw over somewhere over here, the phase space factor, which was defined as a Q star over 8 pi E star, and the symmetry factor here. Here's some explanation of where it comes from in quantum field theory. You can ignore it unless you want to give it a try. Give it a try. But it's defined right here. And I define it in terms of S, again, just to make life easy. Instead of having E star squared everywhere, just have S. So this kinematic factor here, there's some more exercises. Here I'm dealing with identical particles throughout, so this Cassie factor is 1/2. The phase space factor is Cassie symmetry factor times QCM divided by 8 pi squared of S. And again, some plotting routine to plot the phase space function. And you see it's the square root function, but now it's not just the square root because there's also some other factors in there. So it's discontinuous across the real positive energy axis, which is what we want. All right. The next section is about the on-shell scattering amplitude, and I write here 2 different forms. One is in terms of the K matrix relation, which I showed, and we're in this limited energy region where we're above the 2-particle threshold, but below any inelastic threshold. So any other particles that can be produced. There's the phase space, there's the K matrix representation and the phase shift representation, which just using the relationship between the K matrix and the phase shift delta, you get this relationship out. And so far, this is just generally what every scattering amplitude has to look like for any type of interaction. Now, this notebook looks at 2 different parameterizations that are very useful to discuss low energy physics and physics of bound states or resonant states. So one is the effective range expansion, which is this Q cotangent delta here. Since there's no imaginary part in this function here, it's a real function. You can use Taylor expansions to expand the function in terms of the momentum squared, let's say. And when you do this, if you took quantum mechanics, I hope you at least saw things like the scattering length and the effective range. So Q cotangent delta can be written as a power series expansion. Here I'm going to truncate at second order, where the leading order term is given in terms of the scattering length, which is this A here, and this characterizes the strength of the interaction. And the second term here, proportional to Q star squared, is 1/2 R, and R is the effective range, which characterizes the range of the interaction. This parameterization is very useful for describing strongly interacting bound states, of which the deuteron is an example. So while we still don't know what specifically A and R are, we can then use this parameterization to fit to data in order to determine what the scattering length and the effective range are. And then we can make plots once we determine those from a fit, or we can calculate A and R from lattice QCD. That's the goal. This also works for very weakly interacting systems. So if you have, like two pi pluses don't really want to interact very much, and it's a weakly interacting system. Weak as in the forces are weak, not in the electroweak theory. So this parameterization is very useful for those cases. It can be used for any case, but you get more of a physical interpretation out when you think about those cases here. But again, these are just general parameterizations. They don't depend on any specific model. They just lend themselves to specific interpretations, which may be easier for some cases or other cases. Another is the Bright-Wigner. The Bright-Wigner is very useful for parameterizing resonance states, or states which don't live very long, these quasi-stable states. And the tangent of the phase shift is given by this expression here, where you have some pole in the phase shift and this gamma function. This gamma is related to the width. It's not exactly the width it's related to. And this is what I said earlier, that these parameters in the Bright-Wigner function don't exactly correspond to the pole mass and pole width for resonances, but they're related to them. And here you have two unknown parameters here, m naught being the Bright-Wigner mass and g naught being the Bright-Wigner coupling. And these are, again, parameters. If you have a resonating system, so a system with like a narrow bump, you would fit this parameterization to the data via this scattering amplitude representation, and you would get out what those parameters are, and then you can then go to the complex energy planes and look for the poles. And that's what this exercise does here. So here, I've essentially just coded up these different functions here. So I have the amplitude depends on S and the K matrix. The K matrix is a generic function, and the phase space here is this row function here that depends on S. K matrix for Bright-Wigner is defined as it is above, and K matrix effective range is defined as it is above. And then we can plot the amplitude for some cases here. Here I give some examples here. One for the effective range is plotting the effective range parameters. I just chose A equals 2 in units of mass and R is 0. This is some example here. And the Bright-Wigner, I chose 2.5 as the Bright-Wigner mass and 3.0 as the Bright-Wigner coupling. And here, this plot here, I'm using lambda captures to say how to plot this thing. If you're not familiar with it, we can discuss that a bit. But essentially, I'm choosing the Bright-Wigner with these parameters here, and you see this is the plot of the Bright-Wigner amplitude. So the peak is roughly at 2.5, and the width of this thing is governed by this coupling G. If we plot this amplitude in the complex energy plane, so now let's just imagine that these numbers come from some experiment, or some theory, we calculated them. So we have this thing on the real energy axis. What does this look like in the complex plane? Well, this is an analytic form for the amplitude here. So I can just now take S to be complex valued, and that's exactly what I do here. So now I define this plotting function, which I dictate here in units of mass squared, the range of S and the range of real S and imaginary S. I form them, I make a mesh grid and form them in the Z equals X plus IY. And I plot the amplitude. And here you see the real part and the imaginary part of this amplitude. So one, you see in the imaginary part, you see this discontinuity. It's exactly what we were saying in the developing the theory for this, that this phase space induces this branch cut discontinuity, and the imaginary part has this discontinuity here. The real part doesn't, but the imaginary part does. And you see here, if you look at the real axis, which is at this location here, you see this bump-like behavior, and that is this bump-like behavior here. So then, okay, so then other stuff here is to check unitarity. So here, this just checks that unitarity is enforced. So I'm plotting the imaginary part minus rho times the absolute value of the phase space. You get, that this difference is 0, consistent with unitarity. Playing around with the magnitude and phases, what they look like. And this is the first, and this is just some qualitative features about the scattering amplitude. The next part talks about getting at the spectrum of this scattering amplitude, which is the next part I want to talk about, which I want to go back to the slides to introduce the idea first. So let me ask, are there any questions here before we move back to the slides? And I see, I think I have 15 minutes left. Debating. All right, so let me introduce the idea of the deuteron as an example of getting at some physical quantity from all this kind of esoteric scattering theory I'm talking about, and then we'll end today's lecture and pick up with it tomorrow. So the deuteron will be an example I take you through here with how to obtain a bound state property from some scattering amplitude. So the deuteron plays a role in many nuclear processes. Here you see kind of the low number chart of the nuclides. You have the proton and neutron as the lightest particles, and the deuteron is the simplest bound state. The deuteron plays a role in things like stellar fusion of heavier elements. So if you look at stellar nucleosynthesis, how does this come about from the fusion of protons and neutrons? So if you have two hydrogens, they can interact to form a hydrogen 2, a deuterium nucleus, which then it's hit by another proton to form helium 3, and it releases betas and gammas, which then interacts with another nucleus to create helium 4 and a hydrogen atom, and that helium 4 is what's being produced in proton-proton fusion of the sun. So the deuteron comes about from these interactions of two nuclei, specifically proton and neutron scattering. So we want to quantitatively describe this thing, and we can look at what does neutron-proton scattering data look like. So here is a set of data. If you're interested in where the data comes from, I can point you to the references and data sets. I didn't label them here. So the blue points are the data sets for the cross-section of proton-neutron scattering measured in barns. The x-axis is the kinetic energy of the neutron, because you have a proton that's stationary from some hydrogen gas, and the neutron is bombarding it. The red line is a theoretical curve, which has been fitted to it, and I'll show kind of what the fit parameters are in a bit, to get at the scattering parameters of this thing. So the blue points is what you measure from data. You want to fit it with the red curve and get out some physical information. So what do we know about the scattering amplitude? I'm going to ignore things like the mass differences of the proton and neutron in strongly interacting limit. This isospin limit is what it's called. The proton and neutron are degenerate. So we're going to assume equal mass proton neutron. There'll be some slight corrections to this, but that's for more precision stuff. We're going to ignore details like the spin of the proton and neutron and just deal with very low energy scattering where the spin doesn't really make that much of a difference. We know that the scattering amplitude can be written in terms of this K matrix and this phase shift here. For the proton and neutron, which I just call N for this nucleon here, the mass is roughly 940 MeV. And Q star is given by this with this symmetry factor for the phase space is 1/2, because we're going to treat the particles as identical in this example. So we can use for this very low energy interaction the effective range expansion for the K matrix or the phase shift, where again I'm going to introduce this scattering length here, which describes the strength of the interaction, and the effective range. So if we use this representation for the amplitude, we can then fit that amplitude to the experimental data. So we can form the cross section by taking the modulus squared of the amplitude and integrating over the appropriate final state kinematics. When you do all that, so hiding all that under the table, you get out that the scattering amplitude for the proton-neutron scattering is given, it has some curve like this. 0 here is the threshold point, since I subtracted the 2 nuclei mass. And you get out these scattering parameters, where the scattering length is roughly 5.4 Fermi, and the effective range is 1.7 Fermi. And a Fermi is roughly 1 over 102, is roughly 1 over 200 MeV. So this gets you an example of fitting experimental data in order to get at to get at the physical parameters. And, so here you're going to get some strength of interaction and some range of interaction here, which is roughly 2 Fermi, which is the characteristic scale of this deuteron. So where is the deuteron hiding in this proton-neutron scattering amplitude? Well, we have to look at the spectrum, which is looking at the pole singularities. So the proton and neutron can bind to form the deuteron. The deuteron's a bound state. Bound states appear as pole singularities below this threshold. So the deuteron should appear below the twice m here. And pole singularities, again, look like this 1 over x form. So the deuteron should be hiding in the scattering amplitude when we push the energies of the scattering amplitude below the threshold value. So if we do that, we can do it analytically, and we can also do it numerically. The exercises in the notebooks can do both, where if you go below threshold, the momentum is no longer real. It becomes imaginary because it's not real momentum. And we can define this binding momentum as the part proportional to the imaginary part. The mass of the bound state is simply equal to twice the square root of m squared minus kappa squared. If you put in the q star squared into this, would be the corresponding mass of the bound state. And the bound state mass has to be below the threshold energy, which is twice m. And the binding energy is simply the difference between these. So taking these parameters here, we can look for the pole position. And we have an analytic representation. So the pole position of this thing is going to be where Q cotangent delta is going to be equal to IQ star. So that's where this function blows up. When we do that, let's assume that the scattering length is the dominant contribution. In actuality, you would need to take non-zero effective range, but just as a simple example, this means that Q star cotangent delta is equal to -1 over A. So you have -1 over A minus IQ star. That has to be 0 for where poles occur, which means Q star must be I over A. So now we know A, so we know what Q star is. The binding momentum then, as we saw for bound states, the momentum is imaginary when we go below threshold. So the binding momentum is simply the part proportional to I. The binding momentum is roughly 37 MeV. Therefore, the mass of the deuteron is roughly 1878 MeV. And the binding energy then is the difference between threshold and the bound state mass. And that's roughly 2 MeV, which is consistent in this kind of approximate universe here, just dealing with this simple picture, with what the binding energy is of the deuteron, which you can show is 2.22 blah, blah, blah MeV. So this is an example of how to get at bound state properties from scattering physics. And the rest of this notebook, and I'm really running out of time, I apologize. The rest of this notebook, after the unitarity checks, goes through some examples of bound states and resonances. So for the effective range parameters, too far. For the effective range parameters I give here, this A equals 2 will give a bound state. And you can show, and that's what I think is done here. Oh, no. So what's done here is the resonance case. But so the resonance case is a particle on the complex plane. And there's some discussion about doing the analytic continuation for resonances. I don't have time to talk about that here. If you have questions, ask me. Unfortunately, I don't have enough time. But if you look at the bound state case, so the effective range, you can show exactly numerically what we were talking about there in the case for the deuteron. If you put in the deuteron numbers, you'll get out what I was showing before. So let me stop here. I probably went over time with this discussion, but I wanted to kind of get more through this so we can get to the QCD part tomorrow. So let me take questions here. I apologize for kind of rushing through some of this. Are there any questions?
So around where exactly do you fit, like in which section do you fit the parameters in, the
Yeah,
A
so
and the R parameters? Yeah.
so the fitting is not in this section. I was because originally I created these things to not discuss about where those numbers came from. But this morning I decided to show this plot. I'm planning on writing an exercise notebook with the fitting of the neutron proton parameters. This GitHub will be will be around for a while. So if you're interested, once I get that done, maybe you can, if you're interested in that information, email me here and I'll make sure to send that out to you when I have that finished. Because I don't, I only started thinking about doing that exercise recently. So I apologize for that. But I do have some, so you can see here some Python code to do it. But it's not for public consumption yet because I was just trying to fit around the parameters. So yeah, the fitting is not in
No.
here. Yeah.
Yeah, it's all right. Thank you.
Yeah. But yeah, if you're interested, ping me and I'll send that out to you when I can because I'm preparing it for another uh, lecture in the coming weeks, so I'll be getting done with it soon. The other lecture is more geared towards actually doing some fitting, and I didn't really want to talk much about fitting in this case because other people talk about fitting, but yeah, thanks. If you're interested, yeah, I'll be happy to send you that once it's ready.
Righty then. Thank you again for the talk. I'm going to go ahead and stop the recording now.